Okay, so we can get a high surface area, but why do we care? I mean, it's kind of a neat trick, but why does it matter? And the best example to exemplify this is coffee. Think of a couple different ways you can make coffee. You can take a little drip machine. So, take a drip coffee machine, which has a coarse grind, so our little green fluorescent particles there, that's our coffee, and it sits in hot water for a decent amount of time. I mean, it's kind of a long soak for the coffee to sit in there. So we have large pieces of coarse coffee so that it doesn't turn bitter, basically. We match the size of the coffee to the temperature of the water and the amount of time it takes for the water to go through. An espresso machine, however, uses steam. So the water is really, really hot. It's above 100 degrees Celsius. And it's forced in there for a very short soak, maybe like 30 seconds. So how do we make sure we get all of the flavor out of our coffee even though it's only going to be exposed for such a short amount of time? We make it smaller. We grind the coffee beans into a much finer powder, finely ground coffee, and that allows us to get all the flavor out in a shorter amount of time. So the drip coffee is your idea of a low surface area, slow reaction between the water and the coffee. The espresso is a high surface area. We get a very fast extraction between the water and the coffee. So it's a high reaction, let's say, a fast reaction. Let's put something a bit more typical in this in terms of technology. Graphite. We're going to take graphite and we're going to put lithium in and out of it. So it's a lithium ion and it fits in between the planes of graphite, kind of like between pieces of paper. Now, the lithium can only go in at a surface and it has to diffuse through the graphite in towards the center. So, and that rate at which the lithium can go in and out is what determines how quickly you can get power out of your battery. So if you're trying to use this for an electric vehicle, you want as high power as possible. If, however, we were to cut apart our graphite into smaller pieces, we get a higher surface area for the same amount of mass, and we have more sites for the lithium to go in and out of. Additionally, because the pieces are smaller, there's less of a distance that the lithium has to diffuse through. The result with this higher surface area is that we have more reaction sites and we have a much shorter diffusion path. Both of those taken together means we have a faster reaction kinetics. This is a big deal for energy. It means for the same grams, the same amount of battery material, so the same amount of charge stored, you can get more power. Okay, so surface area is great, but how do we measure it? I mean, how would you measure something that has the surface area of a particle? Well, there's some options. There's a laser particle sizer, which basically takes particles, hits them with a laser, and measures the angle at which they are deflected off. The problem, though, is that assumes that you have spheres, and it requires a powder to test. We don't want to test a powder. We want to test a gel, a bulk monolith. What about SEM? Just look at it. Just look at it and take a picture. Unfortunately, SEM is a spot analysis. You're looking at one piece here, one piece there. You're not getting an idea of the whole picture, so you don't know if you're seeing the entire thing. You're also usually assuming that you have spheres. So, to the rescue is gas adsorption. Or another name for it is BET. We'll get into what that means. It's actually three guys' initials. So gas absorption is a direct measurement, for the most part, mostly. I'll show you where it fails in a bit. But it's the most direct measurement we have. Okay, if you're writing this, copying notes on your own, start a new page with this. This is a cross-section. There's three of them. They're the same cross-section, though. We're going to show over time. of your material showing the top surface. And we're going to list that just that top one is in vacuum, so there's no gas stuck onto it, it's just bare. We're going to make some graphs as we go along this too, and the axes, just label them for now. The partial pressure, so P over P naught, and the vertical axis is a quantity of gas adsorbed. So how exactly does this work? How do we know? Take PV equals nRT, the ideal gas law. You know the pressure and the volume, you can predict the temperature, or vice versa. Suppose we start from pure vacuum, there is no gas molecule stuck onto the surface, and we administer just a small amount. We administer some number of molecules n and let them sit in the same environment as our material. We know temperature, we know the volume, and if we know n, we can compute the pressure that we expect to read. It should be the pressure as this gas is allowed to expand. The difference, though, is that that pressure is always, always, always less than expected. The pressure that we read, that we actually measure, is always less than the expected. And that difference in pressure is due to a number of the molecules are now stuck onto our surface. That's what we mean by adsorption. It's molecules getting stuck onto the surface of our sample. So, if they're stuck onto the surface, they're not up in with the rest of the gas, bouncing around and contributing to pressure. They're taken out of the pressure equation. So, that difference in pressure can go into PV equals nRT, and we can compute the number of molecules that are stuck. So how do we actually go about testing this? Well, dose in a little bit of nitrogen gas at a time, and some of it will get stuck onto the surface. So if we graph this now, let's look at, we've been testing for a little bit, and we're slowly increasing the pressure and watching how much gas is being absorbed as we go. We do it divided by P naught, by the partial pressure, because that's the point at which it starts raining nitrogen inside there. So the partial pressure and the quantity absorbed. And what we're looking is for when it plateaus. Because when it's a saturated surface, so now we've saturated everything with a monolayer of this nitrogen, no more can fit inside. That means that well, I'll show you why we want to know that, but we want to know basically why, at what point is the surface completely saturated. Now, as we're saturating the surface, when we've reached that, that's basically a plateau in this line, because no matter how much we increase the pressure, no more gas gets absorbed, until finally we increase the pressure so much that it starts raining nitrogen, and it looks like a whole lot of nitrogen is being absorbed, but in fact it's just making liquid, which is not really the same thing as getting stuck onto a surface. So we're looking at that plateau right there. That height tells us the actual number of molecules that have been absorbed onto the surface. How do we convert that into an area? Well, we know that one molecule of nitrogen has a certain area that it occupies. So one molecule of nitrogen takes up 0.162 square nanometers of space, because it sits in its own little area, but it kind of vibrates around, so it has basically a personal bubble of 0.182 nanometers that it takes up. So if we take the number of molecules that are stuck onto the surface and multiply it by the surface area per molecule, we get the surface area of our sample, if it were an ideal case. Unfortunately, it never works out that nicely. So let's redraw those three samples, again, three surfaces, to get a visual description of what actually happens. First, we never start from a pure vacuum. There's always some gas that's kind of stuck on there. That throws our equation off a bit. Second, it doesn't always go down evenly and nicely distributed. The gas will clump together in certain areas, and it may even build on top of itself. And then that saturated surface, the point at which it levels off, might not be a nice monolayer coverage. In fact, it almost never is. There'll be places where parts of it are stacked on top of itself, So we have nitrogen on top of nitrogen in a multi-layer arrangement. And even there'll be some of the very small pores that are actually filled with liquid. That also throws off our calculations. So that's why it's only mostly a direct measurement of the surface area. And that's where those three guys came in, and I forget their names, but BET are their initials, which is what this is named for. They came up with a model that accounts for all those little differences and the deviations from ideal to actual. So in summary, when it comes to sol gel processing, and specifically how do you dry a sol gel, it's difficult due to those capillary forces that occur when the solvent inside the gel tries to evaporate. It collapses the structure. Now we can dry it into either an aerogel, cryogel, or Xerogel, and those are in order from both high to low surface area and most expensive to least expensive. The processing of an aerogel is about doubles its cost. It's pretty expensive. We care about surface area though because it usually determines the reaction rates of pretty much every chemical reaction, at least ones that occur with a solid. Now, the best way to measure the surface area is to use a gas absorption technique. It's the best tool that we have for measuring surface area, but it makes some assumptions inside that model which increases the uncertainty of it. So it's very useful as a comparison tool, and it's the best one we have. That's everything for today. I'll see you on Wednesday.